Cool. All right, guys. Yeah, the talk is about building voice AI agents with as low latency as possible. So both Omar and I will give different parts of the talk. He'll talk about LLMs, latency, and then I'll talk about the FSM that we've built in order to control the conversation. So this is who we are, a little bit of our background. We're both at Synthflow for a little while, you since
November last year?
No, November of 24, right? Yeah. And been here for about 7 months, June of mid last year. We're a relatively young company, and we built these voice AI agents for customers.
Cool. So I'll start with part one. Why did we use Go for voice AI? We actually had at the beginning we had another prototype of the voice AI.
Sorry. Can meet us so this can.
Okay. Yeah. So at the beginning we had another prototype of the voice AI. It was another language. Then we tried then we decided to switch to Go. Why? Because we make thousands of simultaneous calls. I think our average day we make 100,000 calls. And having a low weight concurrency patterns helped us scale this. Also, we felt that Go was native, it felt like it fit the domain. Using channels for streaming came very handy. Using context for canceling work that is not necessarily anymore also was very handy. With that, also with a low overhead with the threads, with the goroutines. We aim to achieve 2.8 seconds of latency. So once the user says something, we need to answer that user within 2.8 seconds, because anything higher than that feels a bit laggy. The customer thinks that the bot stopped answering, right? Or it just doesn't feel natural anymore. Our pipelines, it's not just that, but the simplest version of our pipelines, it's user says something, we transcribe that to text, we then send that to the LLM, LLM generates a response, we speak that response, we generate an audio, and we send it to the user. We basically have goroutines that run each part of this this pipeline. And the thing is, it's not one-way flow, right? A user can, at any point, for example, say something that would interrupt the entire flow. So we need to react on that, cancel something that was already in flight, and deal with that. We use channels to communicate with this goroutines. And LLM itself is not very reliable. Sometimes it takes longer time to process the same prompt. Sometimes it takes less time. So we have to deal with this non-deterministic latencies that LLM throw at us. So gonna talk about the LLM latency. So for example, when we have the cases when we had earlier, when the LLM would pause, the user would think that our chatbot died, but it actually didn't die. It's just the LLM was a bit slow. What did we do? So, the key metric that we keep track of is TTFT, which is time for first token, and that's very crucial for us because once we generate the first bit of the audio, the user is engaged. The LLM can take much more time after that. So that's really the crucial part. Even with that, what we also found out is that it's not just the first token that we care about. We care about the first audible, the first bit that we can generate audio for. For example, the LLM can generate a long text, but we would want to finish where, we need at least the part where there's punctuation, because that would allow us to generate audio for that bit, right? So streaming stalls mid-sentence. As I mentioned, we could get the first token, but still the whole audio, we could not generate audio for that because we did not get to a punctuation point. Also, we noticed that the LLM latency generated varies by region, load, and sometimes it's just random. It really has nothing to do with region or load. It just decided to take much more time. And the same endpoint, so we use multiple endpoint of the LLM, for example, on Azure across 20-25 deployment. We use them, and we still notice that the same endpoint sometimes is fast, sometimes slow. We had to deal with that. So the first solution was like a very native Go solution, which is like the fan out. We raised multiple LLM requests in parallel, and then like the first one that gives us a response, an audible response that we can write an audio for, wins. And we cancel the rest of the work via the context. So context here became very handy because it just works, right? This solution helped us improve our P90 significantly. I mean, this is what the solution looks like. We have a bunch of requests that we fire with hstream, and then the first one that comes kind of kills the rest. We cancel them, and we cancel their contexts. But this wasn't enough. Just because we were able to improve a little bit, this was not enough. We wanted to achieve, we wanted to achieve a better solution. Here comes the latency router. So it's a component that keeps track of how much each endpoint's latency is, right? For example, maybe if we hit the US in European time zone early in the morning, it would be faster than hitting the European endpoint because Europe maybe has so much traffic, but the US by that time has no traffic. That belongs, that decision comes back to the latency router. It registers all of these routes that we can call and can tell us which one is faster, which one is not. So the latency router tracks response time, tracks errors, best endpoint for a model, and it caches this for 30 seconds. And then every 25 seconds, we kind of just warm our cache, keep up track with the latency router. We report stuff oh, this took this much time, the first token took this much time, this did stall midway, or it did not. And this way, the latency router itself can learn as our platform keep doing the work. We have set up the latency router to give us 90% of its own data, and 10% it explores. So for majority of the calls, we get the best decision that we know we can have, and for 10% we try to kind of discover a new fastest route. So we don't kind of stick in a best, and not the best, but minimalistically the best position. We also kind of implemented a weighted averaging. So we don't just care about the last 1 hour of these latencies, but we care about the most recent one. We give it a higher weight, and then we kind of the earlier ones have a less weight, right? And if something fails, we kind of forget about that endpoint for a whole minute. I mean, this implementation really helped us a lot. We found out that after implementing the latency router, we were able to achieve our 2.8 seconds of latency and much more. I think then we come to the next part.
Yeah, so our latency router also improved reliability. So because we didn't rely only on one endpoint or another, when you had isolated blips of high latency in one particular region, we could fail over or use and exploit different regions, and this was done seamlessly even within the same call. So if one region started seeing a lot of traffic, we could use US East 1 instead of EU West 1. Cool. All right, so we're coming into FSMs. So FSMs, for those of you who don't know, are finite state machines. And this is going to discuss a little bit, we've talked about how we invoke the LLM and how we get the best latency out of the LLM. And we're now going to discuss now a little bit about how we manage the conversation. So when you talk to it, how do we decide what to say next? How do we decide what to do next? And we need to actually make the LLM useful now. So that's how what we use FSMs for. So the problem is LLMs are non-deterministic, but our business processes need guarantees. Customers aren't happy when we transfer somebody, but they say, oh, we need their income to be above a certain threshold, and they got transferred and they never even talked about what their income was, or something Or imagine a doctor's practice where you say, hey, I want to make a booking, and you get to the booking stage before you've actually asked them what their issue is. Well, LLMs can do that. We've seen all sorts of crazy failure modes with LLMs. So how do we make them, how do we give the companies that rely on us the guarantees? The solution is a hybrid FSM. So we define states, transitions, and the required data that needs to be collected in a state machine. The LLM understands language and generates the responses, so that it's in charge of having a conversation with the user. And the LLM, we also defined a command language, which is custom, and the LLM uses this. The FSM execution engine will then validate the commands that the LLM generates and then execute on those. So we sort of get this hybrid build structure that we designed for our use case. So you won't find this out in the wild anywhere, but it's defined internally. So we start the important parts here. We're not going to go through all of it, but and this also doesn't include other, because it's otherwise quite large. But the important parts here are the states. So we have multiple states, and we have transitions with triggers, targets, and conditions as well. We have different types of conditions, and we'll get into that in a little bit. But the important part is, where do we start, and how do we end? The end isn't in here, but how do we move between the different states, and then how do we eventually end? So this is the FSM structure that we have. So some FSM concepts. We've got different types of states based on what the bot can do. There's the utterance state, slot collection state, there's also action states, and terminal states. So utterance is just say something. Naturally, you want it's a voice AI, should talk. Slot collection is you want to collect information from the user, right? Their address, the value of the property they want to buy, anything like this. And terminal states, so you want to end the conversation. We have transitions between those. We've got the trigger, the target, and the condition. The trigger is when do we evaluate this. The target is which state would we move to, and the condition is if we move to that at a particular time. So you could run the trigger on every response from the user. That would be less efficient. You can run the trigger in an action success, for example, or an action failure. We're going to run that condition. There's different ones. Slots are type variables collected from the user. We've got various different types: strings, bools, enums. Strings are very common. Bools, yes or no. There's also integers and enums. Enums are also very useful for branching. So if you want to make conditions that branch to different states, you can use an enum. It's very common. And then we have the conditions. We have two types of condition evaluation forms. We've got the deterministic or expression evaluation. And we have LLM evaluated, which is using a prompt condition key within our FSM. And this gives customers the flexibility of, do you want to have like hard logic about which branch you're going to take, or do you want the LLM to decide? And this is very convenient. A lot of customers, like we only had the expression evaluation for a while, and everyone was trying to use booleans, like, is the user happy? Yes, no, Did the user do something? Yes, no. And you're like, everything becomes a yes, no, but it's a bit of a pain. So prompt conditions, LLM evaluated conditions allow more emotion to be sort of involved in that branching, and that's quite cool. How do we prompt in an FSM world? So the prompt is, we prompt the LLM in a similar way to prompting, we call it simple prompts. We just throw the whole prompt at the thing with the conversation history. We give it a bit more information though. We give it the current state, we give it the available transitions that it can make, and we give it the slot definitions, so the variables that are there. So this is kind of giving it the context, the current context of the conversation. The transitions have a condition or a prompt condition, which the LLM will need to evaluate potentially. We give it instructions on how to evaluate those conditions if they're present. The flexibility to use expressions when possible, natural language when needed. That's the condition and prompt condition. We also explain to it what not to do, and we give some examples as well. So if you've ever been prompting LLMs, you know they can sometimes go a bit off the rails. So we give it some guardrails and some examples of those, importantly. Especially for action calling, we give it action calling examples. It needs to use arguments and things like this. Important for bookings. Also, it sometimes tried to make bookings in the past, or like at the turn of in December, tried to make bookings for the beginning of 2025, and it's coming to 2026. It doesn't really have, especially the older models like 4.1 and some of these things. The newer models are better at this, but you really the prompting varies a lot in the model. And when we're going for latency, we try to use the smallest, as close to dumb model as possible because they're usually the fastest. And then the command ordering is also important. So we explain to it that you want to set slot, then trigger next step, and then utter. And I'll explain why in a bit. So this is a bit of the command protocol that we have. So we've got set slot, name and value to store collected information. So it can call set slot, utter with a reason. And it will speak speak something to the user. The reason is useful because it allows us to sort of classify different types of utterances. So like, are you trying to collect information? And we can show this in the UI. We can put analytics to this. It's a flexible field, but the LLM can choose what to put there. And it does come in handy. It also gives sometimes some insight into the thinking of the LLM about why it said the things that it said. Execute action with the name of the action and some parameters. This is similar to like tool calling. If you've ever seen tool calling, this is our own tool calling. The next step and then the next step name, which is to request a transition. Now there's two different, the next step will not actually hard go to the next step. There's two ways this can be executed depending on what sort of condition is used, but this began as just an assessment, and I'll explain why this wasn't actually executed. It was used to understand the thinking of the LLM so that we could optimize for latency. So we're going to come to how we parse the commands, how we turn LLM output into actual commands. Well, first we need to clean it, strip out all the stuff that LLMs love to put into output, like bullet points, quotes, and these things. Regexes per command type, and we just skip unpassable lines. Everything here has got to be best effort because we need to reply to the user. If we don't reply to the user, or if we don't get a valid command out, we need to try again, which adds latency. So everything here is as close to best effort as we can get, while still being able to maintain good functionality. Utter requires a semantic reason. Again, it can explain, and we can use that later on. And we have some graceful degradation. So valid commands will still execute while invalid ones won't, this sort of thing, because we need to maintain some behavior. Otherwise, the user is going to be sitting there waiting for a while, and we're not going to do anything. And that's terrible. So when we're parsing the commands, there's a few things we need to take note of. So the LLM will send a set slot, let's say it says set slot email of something, and then next step, verify. So I want to move on. The verify requires the email, but it's not set yet when we validate. So we need to project what the state will look like when we do that validation. So we need to essentially take the current state, project what the state will look like, run the validation conditions, and then see if we can move on to the next state. So this is projection. Build the projected variables, validate everything works, and then execute if everything passes. Otherwise, don't. We have the two-phase command processing. So this is, we have two different types of the next step processing. We have the assessment and the execution types. Assessment, and this allows us to prevent having to make a second call to the LLM in order to generate something to say. This ensures that the LLM has correctly predicted where it's going to go to next and generated a response that is valid for that. It knows sort of where it's going, and this makes the conversation much smoother. If we just say to the LLM, only generate something within your current state, and not considering the future state, what it says can be pretty unnatural at times. Like, I'm going to execute the action, and then it will do the thing, rather than, oh, I executed the booking action, and it went well, and here's your booking. There's probably better examples of that, but that's what we do. The execution is deterministic, assessment is LLM judgment, validate the assessments against the projected state, and if it's invalid, we'll attempt a correction. So if the LLM made an incorrect prediction, we will make a corrective call to the LLM, and we will tell it, hey, your prediction was wrong. Actually, maybe the condition that we have, when we evaluate the condition, we come up with a different answer to what the LLM predicted, because the LLM is not very good with hard logic. And so we will make a corrective. If the LLM thought, oh, the person is over 18, right? And it says like, oh, wow, you're good, you can buy alcohol. And actually, we evaluated the condition and we know the user was actually 17 or something, then we can't say, you're good to buy alcohol, right? We need to now make another call, generate a new utterance, and then play that to the user. So it takes longer, but by doing this, we can save that extra call 99% of the time. And this is it. So we aim for one round trip. We aim for one round trip to set all the information and generate the next thing to say. And that is using speculative execution. Similar to if you've done CPU work, CPU speculative branching and these sorts of things. So like if conditions are true, then do this and load things from RAM depending on which whether condition evaluates to true or false. And that's a similar thing. But sometimes then you need to throw out that answer, right? That's also a downside, and then do the work again. But most of the time it's pretty good. So yeah, this is minimizing the LLM round trips. Every LLM call adds latency, and we need to keep that as low as possible. If we get everything in one call, we execute optimistically. LLM returns, set slot, utter, next step together. The utterance is sent to TTS immediately, and we don't wait for validation. If there's a next step and it's valid, we do the one round trip. If it's wrong, we skip it and we correct. So that's two round trips. So when the assessment fails, we'll still execute the set slot, but the utter is skipped. And we need to ask the LLM for a new utter. We still execute everything else, but that is, so yeah, here's an example. Avoid saying transferring you now when the transfer is not on, right? That would be kind of silly. But we pay for that with a little bit of extra latency. Our correction loops have a circuit breaker, so if the email isn't corrected and we need to make a corrective utter, we will try again, but we will attempt it up to a maximum of 2 correction attempts, and if those fail, then we fall back, and we fail gracefully to predefined responses. So that's the next pattern that we're going to cover is the slot values. So this one's pretty simple, but is very useful. So we need to also tell between whether or not we've collected information or not. And we use a similar pattern to SQL null. So if you use SQL null string or things like this, we could choose a pointer here, but is nil not set or not collected? So we use a slot value with a value and collected true false boolean, which is the same thing. Context without cancel. So because all of our work is highly asynchronous, there are some things that we need to be very careful about whether work will be cancelled and at the end of the turn. So we have turns for the user, the bot, sometimes bot, user, bot, these things. When we create a context for each turn so that we can clean up the resources afterwards. But there is some work that we want to persist and continue to do even if the turn ends. So when the user interrupts, we start a new turn. But if we're creating a booking in the system and the person interrupts and we cancel the context for that booking call, that's not great. So this is important, context without cancel. Done will return nils. So we're basically able to decouple work that we want to continue running, even though the turn has now been cancelled, and we use this. And then the solution to preventing it from hanging forever is we have specific work isolated timeouts. have that on the context for just that work, but we decouple it from the terms context. If we get that wrong, then it can cause issues. It's not always trivial. We have had issues where the person will interrupt and will cancel actions, or an action will finish, and it's not easy. Message buffer back pressure. So we need to sometimes not allow the user to interrupt the bot. And the way we do this is by but we then need to reply to the user after the bot is done speaking with a context relevant response. And we do that with a simple buffer. We append the user's speech to a buffer, and then we flush it at the end of an uninterrupted return. So this would be something like some sort of mandatory message that needs to play to the user in particular scenarios that cannot be interrupted. But the user can still speak during that time, and we'll respond to it after that message is played. We also have subflows within the FSM. So if you can imagine, processes can invoke other processes, and we have a stack for this. So if the user some customers want more flexibility within their flows, so we give them these composable subflows, which they can invoke with certain triggers. In order to do that, we push the current stack or context to a stack, and we inherit certain things like variables, just variables, and we create a new execution context, which then we start a whole new FSM and execute that, and then at the end we pop that from the stack, load the old context, and continue execution there. So the stack frame holds the FSM definition itself, the execution context, variables, and the parent reference. It's inspectable for clean unwinding. The input binding, so we bind the parent's variables to the child's variables, and we also need some output sometimes from those, so we can bind the child variables and pass them up the stack, similar to function calls, really. It's all just the same thing in a different form. And this allows us to have clean restoration of the parent flow when a subflow executes. And this, you could have nested subflows, so you could have a subflow called a subflow called a subflow called a subflow. At the moment, we just have the main flow called a subflow, so we don't really need a stack, but hey, if there's room for expansion, and it was fun to build. So. The real-time voice timing. So these are some little quirks about building in a voice AI world. Some things that at least I, coming to voice AI for the first time with Synthflow, found relatively interesting. So interrupts when you're speaking. It's not trivial to know when someone actually stopped talking, and if someone interrupts the bot, you need to be able to detect this. And we need to know if the bot is mid-speech before stopping TTS, these sorts of things. Then there's the interrupt blocking, so we require, interrupts are kind of knowing when the user goes like, or these sorts of things. You don't want the bot to just stop doing what it was doing, right? So we have also configurable numbers of words to be able to actually, before triggering an interrupt, so that the user is not going to stop the bot from responding to the person. Debalancing as well. If the person continues talking while the bot is talking, there's a bit of an overlap where you may get a lot of different, you may get a lot of interrupts which are triggered. So we debalance those. Silence detection. So there's various different layers to being able to work out when the bot has stopped talking, or when the person has stopped talking. So this is also in pointing. This is also really not trivial, and we have some configured rules for this, like heuristics, and it is machine learning, the machine learning approach where you use a model which is trained on in pointing detection. So we then have certain conditions where we will wait for a little bit longer, such as phone numbers, emails, need more time when someone's speaking out any of these things. We need to be able to detect that and give them a little bit more time to maybe 5, 3, to, if you use traditional endpointing for that, then it can interrupt the user. And these need to be tuned in production. There's no real good way to say this is the value that this needs to be. It needs to come down to feel, and what works for someone may not work for somebody else. And this was very evident with one of our big customers who had much larger prompts. Our timeouts for our LLM were tuned for a particular group of customers. Then new group of customers came in, and their calls were taking longer because they had larger prompts, and that was causing the perceived latency, because we made multiple trips, to be higher for them. So, but then when we fixed it for them, then some other group of customers then suffered. So doing it perfectly for all of them at once is an art, not a science. Cool. Some of the takeaways, Omar, for the infrastructure.
I mean, some of the takeaways that we found out that channels and goroutines were really amazing fit for the domain. The fan-out process that I mentioned earlier and the latency router helped us optimize latency on the LLM so we could serve our customer better.
Yeah, very much. And then the FSM and the patterns takeaway. So the FSM gives us the hybrid FSM and LLM. The two together gives us the determinism where we need it, and it gives the customers flexibility where they want to. We parse the LLM output like untrusted user input, and it's all best effort. So making sure that we, at every potential failure point, we consider what the best graceful degradation or fallback would be. The projection pattern to validate against the future state, not the current, with speculative execution to avoid extra latency with a single round trip most of the time. And the two-phase processing, so we have some determinism or some LLM judgment, and then the correction loops with the circuit breakers to make sure that we don't get into an infinite loop trying to correct ourselves. That's it.